Thank you for the students who sent the email, because of the email I noticed that I was disconnected. Right. Right. So I was explaining all this. Do you see the slides? Yeah.
Yes.
Okay. So I said this is a continuation of the previous lecture, and then we will do a tutorial for both. I can say that this is the most important lecture about VHDL, which is the VHDL modeling styles. So when you work with VHDL, if you have a circuit to describe using VHDL, the first thing that you need to do is to decide which style you need to use, because we have different styles, and each style is suitable for different types of circuits. So for example, if you want to do combinatorial circuit, then you need to select one of the styles that we have. Same for sequential, and so on. So the styles that we have is behavioral design style, data flow style, and structural style. For each style, we have some statements to use. Some statements, we use them in behavioral, we don't use them in data flow. The ones that we use in data flow, we don't use them in structural, and so on. So, and those statements are listed here. So this is the first thing that I will do. We will talk about the statements that you can use in those design styles, and then we will cover the styles. So for example, concurrent signal assignments are used in data flow style. Component and instantiation are used in structural style, and the remaining two are used in the last one, behavioral style. Right, so and then I moved here. So those are the short description of each style. So as you can see here, the behavioral style, it says that the circuit is described as an input-output relationship using sequential statements inside the process. So we use sequential statements inside the process. Sequential statements are, you know them. Those are the if statements, the loops, while loop, for loop, and so on. Those are the sequential statements. In VHDL, if you want to use those statements, which you can, you need to use them inside a process. So first you need to create a process, and then you can use the statements. So we'll explain this first. How do we create a process, and then how do we use sequential statement inside the process? And then how do we use it in a behavioral design style? Is this clear? This design style is suitable for sequential statement, circuit, sorry. We didn't do sequential circuits yet. I think we will start in the next two lectures. So this style is suitable for sequential circuits. We have data flow. I will move to data flow, and then we'll explain the other one later. Data flow circuit is described using concurrent statements. So we need to use what we call concurrent statements. We have three types of concurrent statements. So I'm going to talk about them, and then you can use them inside a data flow style. This style is good for combinatorial circuits. So all the circuits that we did so far can be described using this data flow style. Is this clear? Are you still with me? Yeah?
Yes.
Yes, doctor.
Okay. And then we have the structural design style. Structural design style can be used for sequential, can be used for combinatorial. When do we use sequential, structural, sorry? Structure in structural circuit is described as a network of interconnected components. So basically, you will observe your circuits. Do you remember the last tutorial that we did? We asked you to do a circuit that has 3 2-to-1 multiplexers, right? Do you remember, right? So
yes.
it's the same component. It's 2-to-1 multiplexer used 3 times in the circuit. So when you describe this circuit, you don't need to go and describe 3 in one code. You describe 3 2-to-1 multiplexers. You just take one, you describe it as a component, and this is what we said, component. So you declare it like the use of functions. You can create a function in C or C++, and then you can call it as many times as you want inside your main function, right? You don't need to write the code again. You can just call it by its name, and you pass the parameters to it, and that's it. So you write the code once. So we do, it's exactly the same principle. We have a component, we create the component, and then we create instances. It's like a call to that component, instances of that component. So you don't need to do it 3 times. So this type, so for example, this is a combinatorial circuit, but I'm using structural design style. So first I describe the component, and then I will use it. I will create 3 instances of that component. And then we have the mix. You can mix between 2 or 3 of those styles. So the main styles are the 3 that we have here. Right, so we'll start with the concurrent signal assignment, which we use in the data flow design style. We have 3 types. We have simple signal assignment, we have conditional signal assignment, we have selected signal assignment. The name concurrent signal assignment this means that you can use them to create parallel blocks or parallel entities in your circuit. And this is the advantage of hardware or using FPGA. So you can have blocks in your circuit working at the same time. I mean, you don't need one to wait for the other to run. It's not like in C++ when you write the code, so it will be executed line after the other. Here, you can create things in parallel. You can have multiple blocks working at the same time. I'll give you a simple example. Let's say that you know a matrix multiplication, right? Yes or no?
Yes.
Yes.
So, for example, if I want to do 2 by 2 matrix multiplication, the result is a 2 by 2 matrix. So if we ask you to write a code in C++ to do this, you will do it with for loops, and the codes will be executed sequentially, and then you can have one element at a time. So this element, and then you calculate, you take this by this, and then you get this element, then you go to the next element, and so on. And this will happen sequentially. I can ask you to design a circuit that do matrix multiplications, which you can do. Now, you can do it a circuit that will work like with exactly the same code as you have. I mean, like with a for loop, and you will have one element at a time. So you can have one block. Here you will have the input matrix A, matrix B, and this will give you matrix C, the output. So A, B, C. The element will go here, same, and then you get here the elements one by one. Or you can have a circuit that have, let's say, 2 blocks together. This will give you row 1 of C, and this will give you row 2 of C. And then you will have A, and you will have B. So you can have a circuit like this. Those two blocks, B1, B2, will be working at the same time. Each one will be computing one row of the matrix. I can have 4 blocks where each one will be computing one element of the matrix. So by doing this, we accelerate the process. So, and this is used especially when we need real-time response or real-time implementation. And that's why we use hardware basically, because we can exploit what we call parallelism. So I can have parallel blocks working together. How can we do this? We can do it with the concurrent statements. Here we have simple signal assignment, we have conditional, and we have selected. So we'll explain I will start with the first one. You are still with me, yeah?
Yes, doctor.
Yes, doctor.
Good. We'll start with the simplest one, which is called simple signal assignment. And we use this. Do you remember when we did A is equal A and B? This is a simple signal assignment. So if I have a circuit like this, let's say that I have two AND gates. This is what you need to do, A, B, and let's say one AND gate and one OR gate. I want to do this circuit, X and Y. So here I can do X is equal A and B, and then I can write another one to say Y is equal A or B. And this is the code that I need to write. This is the Vhdl code. Do you see I'm using two simple signal assignments? And both of them will give me this circuit, and it doesn't matter which one I write first, yeah? And this is why we say concurrent. They run in parallel. I could have started with Y is equal A or B, and then I can write X is equal A and B. And this will give me exactly the same circuit as the top one. So basically it will give me two gates working together at the same time, right? It's not the AND gate first and then it comes the OR gate. It's both, they work at the same time. When I put values in A and B, X and Y will be updated at the same time, right? This is what we mean by concurrent. So those are simple signal assignments called simple signal assignment, and they are concurrent. So concurrent doesn't matter which one goes first because they will run at the same time. And this is the general syntax. So we have a target equal an expression. So the expression could be, for example, A and B. So here we use the operators that I showed you. It could be addition, it could be multiplication, it could be anything. So this is an expression. And this is the target. So this could be a signal, it could be an output port. And again, the order, it doesn't matter. As I explained, I showed you an example with two gates. Which one goes first, it doesn't matter. And this is a very important concept here. Right, now this is a question to implement a simple OR gate. I think it's very simple, an OR gate with 3 inputs. So this is the code. Again, those could be together for the entity, and this is the code. This is one simple signal assignment. F is equal A or B or C. I think this is very simple, right? I don't want to waste time here. Let's take the other example. Let's say that we have this circuit, we gave you this truth table, and we ask you to implement this circuit or to describe the circuit using Vhdl. Is this clear? So the next step you do, you can just do K-map and you guess the expression, right? You know how to do this, right? You do K-map, you guess the expression. Are you still with me? Yeah?
Yes, doctor.
Okay, good. So I did K-map, I didn't put here K-map, and then this is my expression. Again, I don't know why this one doesn't. So this is the expression. Once doing the K-map, and then we just describe the circuit. So I have 3 inputs, L, M, and N, and I have one output, F. I think the entity is very simple. Here I have 2 solutions. I can just work with signals and have multiple simple signal assignments, or I can have just one. I think this is the simplest one. In some cases, you have to work with signals. This one, it's not a must. I think you can just do it in one statement. I think you just follow the expression. So f is equal not L and not M and N all together, or L and M, and that's it. I think this is the easiest one. Just one simple signal assignment. You can work with signals if you want. I think you need to draw the circuit for you to understand the where did we use the signal. So if I do, let me draw the circuit. Have L bar, we have M bar, and then we have M. This is an AND together, right? So L, M, N. And then we have an OR. Sorry, we have first L and M. So we take L from here. We take M from here. And then we do another AND. And then we do OR here. This is the circuit. If we ask you to draw it, this is how you will draw it, right? And this is F. So here, as I told you last time, anything that is not an input-output port, so L, M, and N, I cannot use them. Those are already in the ports. Anything inside that is used to connect two components can be used as a signal or can be declared as a signal. So those two red lines here can be declared as signals. So I named this A1 and I named this A2, and then I use them. I declare them as signals. And remember, this is the best or the right place to declare signals. And then I use them. I take each one at a time. I do A1 is equal this, and then A2 is equal this, and then F is A1 or A2. And this circuit is, or this will describe exactly the circuit. So both answers gives me or give me this circuit. Is this clear? So those two different solutions, and they are both correct. Is this clear or not?
Yes.
Yeah, so I'm using signals. I'm using here 3 simple signal assignments, and in the other solution, I'm just using 1. And again, as I told you, the order is not important here. Here, I could have started with F equal, and then do A1 equal, and then do A2 equal. It doesn't matter. I could have started with A2, then F, then A1. It doesn't matter. The order is not important. And see, if let's say that this is my circuit, I have L, M, and then N. Let's say at this time they are all 0, 0, 0. And then now L changes to 1. Because we have L here, this will be updated. A1 will be updated. And because we have L here, A2 will be updated as well. And because we have A2 and A1 here, and they have been updated, F will automatically be updated. So this is how concurrent signal assignment works. Right. Next one, conditional signal assignment. And you will see in those concurrent signal assignments, it's always a target or an expression is assigned to a target. At the end, it's always an expression assigned at the target. The difference between this one and the simplest one is we have different expressions, and at the end, only one of them will be assigned to the target depending on a condition. It's like in an if condition, but this one is concurrent. So if this first condition is true, then this expression 1 will be assigned to target. If not, the condition 2 will be assessed. If it is true, then this expression will go to the target, and so on. Until, and you see we are using else here, else, until the last one, If the last condition is false, then the last expression, which we can say is the default one. So if none of those conditions are true, the default one will be assigned to target. So at the end, there is always one expression assigned to the target. The one that has the first one that has the condition true, it will be assigned to the target. And that's it. So if I want to use this one, if now we ask you to implement this multiplexer, 4-to-1 multiplexer, using this conditional signal assignment. I think for the entity it's clear, right? We have D0, D1, D2, D3 are inputs, and we have select as an STD logic vector. So because it has two values, 0, 0, 0, 1, 1, 0, 1, 1, and then we have the output. This is for the entity. I think the entity is clear, right? Is it clear or not?
Yes, doctor.
Okay. So I think entity is fine. Now I'm going to use this statement. So remember, we have target is equal expression when condition, and that's it. And we keep repeating this, else, 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 until we get. Now, because you know how the multiplexer works, right? So this will be equal to D0, right? If select is 0, 0. I think from here, M is equal D0 if select is equal 0, 0. M is equal D1 if select is equal 0, 1. Is equal D2 if select is equal 1, 0, right? This is the multiplexer. This is what we know about the multiplexer. So I'm going to use this statement, the conditional signal assignment, to describe this. So I just do, this is the output. Remember, this is the target for our case, is equal D3 when select is equal 1, 1. I started with D3 here, but of course you can start with D0, D1, D2, D3. It doesn't matter, as long as you cover all the cases. It doesn't matter which one you start with. And then it's D2 when select is equal 1, 0. It's D1 when select is equal 0, 1. It's D0 when select is equal 0, 0. Else, if we don't have any of those conditions is true, we assign 0 to the output. So the output is 0. And but of course we will have other cases, right? Because we are using STD logic here. With STD logic, we have 0, we have 1, and we have other values. So we can have other values. We don't know what will happen to the circuit. So in a normal working condition, we will have 0 or 1. But we may have other cases. We don't know what will happen. So this is why we add this last case, else we assign 0 to the output if none of the above condition is true. Is this clear?
Yes, doctor.
I think this is a very good example how to use this conditional signal assignment to describe the multiplexer. So this is the description of the multiplexer. Let's do this and then we stop. I think sorry to take 5 minutes of your time, but just to accelerate a little bit. I will do this and then we stop because this one is a little bit similar to the previous one. So we did simple signal assignment, we did conditional signal assignment, and now I'm going to do selected signal assignment, the third type. The third type is I can say is very similar to the previous one. The difference is just the syntax. How do you write it? So here it's like in C, we have if and we have while. You can do the same thing with them, but it's just the syntax is different. Same here, we have different syntax. So for selected, we use with and the choose expression, and then we use keyword select. And again, it's an expression assigned to a target when this expression is true. I think it's better to do it with the, I will show you this with an example. the same multiplexer. If we do this one, we did it with conditional, let's do it with selected, and this is how we write it. So the condition or the choices is, or do you remember the case statement case in C++? Did you do it when you have multiple cases? So it's similar here. With select, so those cases here that we are listing, I have 4 cases, are based on the value of select. So I put select here. So with select, or with cell, which is my select keyword, multiplexer output is equal D3 when 1, 1. This means when the select is equal 1, 1, then the output should be equal to D3. When the select is equal 1, 0 or 0, 1, then D2 should be assigned to the output, and so on until I finish all the cases. Here, for the default one, for the last one, I put 0 when others. So we can use the keyword others to say for all other remaining cases. So if we don't have this, if none of the above are correct or are true, then just assign 0 to the output. So this will be like the default one. Is this clear? So it's, again, it's exactly doing the same thing, but with a different syntax. And again, this is another implementation of the multiplexer. Here, basically, we are using, this is one statement. It starts from here, and it's very important to understand this. This is all this is one statement. Starts from here. I'm just trying to find a different. So it starts from here. It ends here with the semicolon. So this is one statement. It starts from beginning with it ends with the semicolon. And this is a condition, a selected signal assignment. One selected signal assignment. Same here. It's one statement that starts from here and ends in the semicolon. It's one conditional signal assignment. Those are one statement. So they have 3 statements here, and this is one statement. Starts here, ends here. Is this clear? So this code here, because I'm using conditional signal assignment, that I'm using this, then this means I'm using data flow design style. Right. I will stop here. So this is for data flow. Next, we will cover the components. So we'll move to the structural design style, and I will show you how to create components and how to use them. We'll stop here, and then we'll continue next session, inshallah.
Excuse me, Doctor?
Yes.
Doctor, I have a question about this chapter and the chapter before. Are you giving us just to prepare us for the project, or we will be examined on these 2 chapters?
Which project you mean?
I think I heard you say like you are like preparing us to do the project, or I don't know, something like that.
This is part, those are topics in your course.
So we'll be examined. So in the exam we write the code.
Those are topics, and very important topics in digital electronics. Yeah.
Okay. Thanks a lot.
No problem.
Doctor, we will be writing codes in the exam, or we will be sat on computers, or
you will see the type of questions when we do the tutorials. I think it's too early to talk about this now.
Yes. We're jumping ahead. Thank you, Doctor.
Yeah.
No.
So we'll do tutorials, and you will see the type of questions, and you will have the general idea about the
Inshallah.
what can come and what cannot come. Yeah.
Thank you, Doctor.
No problem. Okay, so do you have other questions? If not, then we'll talk to you next session, inshallah. Assalamu alaikum.
عليكم السلام.